Okay, team, let's keep trucking along. Now we're going to do the next part in our series. Actually, I forgot to relabel this. This is part 3, solving one problem, okay? Now we're going to learn how to use Fourier series, and Fourier's trick to find the remaining constant in our general solution, okay? So this is our problem. Remember, we got 2 grounded plates, 1 hot plate. We got these boundary conditions that we figured out from this image, okay? And in the last lecture, we figured out a lot of constants in a longer general solution. So now we have this less general solution that we know satisfies this problem and the boundary conditions. But we haven't satisfied this boundary condition yet, this one, number 3, okay? There's nothing in particular about this solution that satisfies this boundary condition. We can go through and make sure it satisfies the other ones, though. Indeed, this potential will be 0 when y is equal to 0, because this term is going to go to 0 when y is equal to 0. Indeed, this potential will be 0 when y is equal to a. Again, because if I put a in for y here, this sign term is going to go to 0. And in fact, if x goes to infinity, this term here is going to go to 0, so our potential will go to 0. Okay, so I can check right now and make sure, boom, I've used 3 out of my 4 boundary conditions to get to this solution that I have now. All right, so let's go ahead and do that last little bit. Okay, and it's worth noting the way I set up this problem, I allowed for this V naught, or this hot plate, to have a voltage that depended on y. Okay, so this is worth noting. It can depend on y. An easy solution, the easiest solution would be to let this particular voltage of the hot plate be equal to the sine of n pi over a times y, or some multiplication of that, because then c would just be equal to 1, and we would be happy. Okay, because when I plugged, in that case, right, if I were to plug x equals 0 into this particular equation, c was 1, then we would get our potential at the hot plate back out. So then Vx of y would equal V naught y when x is equal to 0, okay? But that is unlikely, okay? Too easy and unlikely. So we need a better technique to find C for more options for what that voltage could be at the hot plate. Okay, so now we're going to recognize that Laplace's equation is what we call linear. Okay, how do I know that it's linear? Let's let the voltage be equal to the sum of a bunch of different terms with their own coefficients that I'm just calling A here. Okay, so the voltage is a sum of a linear set of terms. Okay, if I were to plug this voltage into Laplace's equation, then I would find, okay, that the solution would also be the sum of a bunch of terms. Okay, and okay, what does this give us? Okay, well, this means we can write our potential as the sum of a bunch of terms that satisfies Laplace's equation. And the whole sum will also satisfy Laplace's equation, okay? So if I can construct a solution to this potential, right? This guy here, I want it to satisfy this last boundary condition. If I can construct a solution that is the sum of a bunch of terms, okay, that are linear, which means there's no squares in here, anything like that. Okay, if each of these terms satisfies Laplace's equation, then the whole thing has to satisfy Laplace's equation. So if each of these is equal to 0, then of course when you add them together, they're all going to sum to 0. Okay, lucky for us, you can reproduce any function as a sum of sine. I thought it'd be fun to just bop over to Mathematica to prove that's true. And so you can make a square wave by adding together a bunch of sine waves. So here I'm just going to run this. We've added together 25 sine waves, and the particular sequence, or what these terms look like, is specific to making a square wave like this. This is called the Heaviside function. So you just can't add together any particular set of sine waves, but this set of sine waves makes a square wave. That's 25 terms, and you can see what the square wave ends up looking like. I can maybe increase the number of terms and see if we can get that to look even better. Yeah, so that looks a little bit better. You always, these little jumps at the end are what's hard to get rid of. Okay, but if I were to really add an infinite number of terms, I would get a perfect square wave. Okay, here's just another example, a slightly different waveform. Again, now we're adding 50 terms that are sine functions, and we're getting a waveform that looks like that. So that's common application. You guys will probably see this again if you haven't already in an electronics lab. Okay, so let's go back to our solution here, okay? So the fact that I can make any function out of a sum of sine functions means that if I've got a potential here that happens to be a sum of sine functions, so there's no reason why I couldn't take my original solution here, my original specifics, this particular general solution, and add a bunch of them together. Each individual term will still satisfy these three other boundary conditions, okay? Each term will. So instead of having just one term in my general solution, I'm going to have a bunch, okay? And I'm going to sum from n equals 1. It actually doesn't have to go all the way to infinity. It could go, depending on what my function is on the other side, it could be even simpler, like I showed you in that last example. But if I define a potential that is a sum of a bunch of terms with a sign in it, okay, that satisfies my boundary conditions, that means that there is a right set of coefficients that will make this sum equal what I want it to at my last boundary. Okay, so then I can specify for the right set of coefficients, or basically the right set of these c values, that at x equals 0, I can find a set that will give me the function that I set at my hot plate. Okay, and the difference here is I can get rid of that exponential term because I've got x equal to 0. Okay, so this is my what's called a Fourier sine series. Okay, and this is my any function. Okay, but we're going to use this fact to find the c sub n, so that we can write an expression for our potential everywhere. So we're going to use this to solve for our last constant. Okay, so now in order to do this, we're going to use something called Fourier's trick. Okay, so I'm going to take what I just wrote down. Okay, so for the right set of c sub n's, I should be able to recreate any potential function that I put on that hot plate. Okay, but in order to solve for the c sub n's, I'm going to multiply both sides by another function, which I'm going to call sine of m pi over a times y. Okay, I'm doing this because it's going to help me get what I want. Physically, there's no reason to do it other than a math trick. Okay, but that's going to give me on the left-hand side, I'm going to get this guy, and on the right-hand side, I'm going to get this. And that's going to be multiplied by one more term here. Okay, so math-wise I can do that. Let me tell you why in a second. Now, the next step is I'm going to integrate both sides between the plates, okay? Okay, so that means that I'm going to take an integral with respect to y of both sides. And again, this is just a math trick. There's no physical reason, nothing about potentials or electric fields that would indicate that I would want to do this particular integral. I'm going to just write the sum a little simpler. Okay. And now I'm going to look at the right-hand side. Okay, so let's just look at the right-hand side of that. Because that's going to give me what I want. I'm going to simplify it a little bit. I can pull the sum out, and I can pull c sub n out. And that's going to leave me with this. Okay, and let's go ahead and look at this particular integral. And I'm actually going to switch over to Mathematica again, and then I'll write down what I did in Mathematica back on the slide. Okay, now I want to talk about orthogonal functions. Any two functions are considered to be orthogonal if when you multiply them together and then integrate, you get 0 over a particular range. Okay, and this is relatively important because orthogonal functions, they can make a complete set. So sine functions are orthogonal. And the fact that they are orthogonal and they make a complete set is what allows them to be able to recreate any function. Okay, so it's a particular special thing about these functions. So for example, here in my Mathematica notebook, I've just defined sine of x and then sine of 2x, and I can integrate the product of those. So I just took two functions, multiplied it together. I integrated it from 0 to 2 pi, and you can see the integral I got 0. I can plot them as well. So this is plotting the product. I can plot the individual ones. Of course, you're just going to get a sine function. But if I plot the product of two sine functions, what I want you to notice is when I'm integrating over this range, I'm taking the area under the curve, and there's as much positive area as negative area. Okay, so these two orthogonal functions, when I multiply them together, it creates this particular new function that has as much area under the curve in the positive direction as in the negative direction. And that's what makes it orthogonal, okay? And by the way, if I were to multiply a function by itself, so now I'm going to multiply the sine 2x by the sine 2x, it's not orthogonal with itself. And of course it can't be, that wouldn't necessarily make sense math-wise. So now if I take the integral, the sum is not 0 if I take the integral of the function with itself. Okay, and in fact down here I can solve this problem to be more specific, like what we're doing in the lecture. So now I've got the functions equal to the sine of n pi divided by a times y. I've just set a to some dummy value. And you can see that as long as m and n are not equal to one another, we get the same situation where the integral ends up being 0. And if I look at this curve, this one's a little complex, but you can still see you get the same amount of area above the curve as below. And if you guys want to download this again and play with the numbers, you can. Okay. If I come down here, I'm going to clear variable a so I can get a symbolic solution. If I integrate the function times itself, though, I no longer get 0. Okay, and you can see up here, if I were to set these two values equal to one another, it doesn't look like it would give you 0 anymore. Okay, so now if I go down here, if they're no longer, or if the n's are equal to one another, Mathematica tells me that for whatever a is, the integral is going to end up being a over 2. Okay, so that tells me that this integral, it's special, okay, it goes along with this Fourier sine series because when I do the integral, okay, from a to 0, it's got two possible solutions. By the way, it's just this part of the integral, not the c part. Okay, it's going to be equal to 0 if n is not equal to m. That's what I just showed you in Mathematica, but it's equal to a over 2 when n is equal to m, okay, or when these two integers are the same, okay? Okay, what does this mean? Well, if I have a situation that where n is not equal to m, okay, then our integral here has to be equal, or the voltage of our hot plate has to be equal to 0, okay? That is the boring solution, okay? And I can look back here and tell why. So if n is equal to m, that tells me that this whole side is going to be 0. So in order for this side to be 0, this term here has to be 0, okay? That's the boring solution. We don't want that. So let's think about terms, again, where n now is equal to m, okay? In that case, I get something more interesting. Then I get the integral that I was left with on the left-hand side, which looks like that, is going to be equal to my coefficients times a divided by 2. Okay, hopefully you guys can see where we're going with this. I'm going to copy this to the next slide. All right, the whole point of doing this, all those math tricks, it gives us to find the c sub n's, okay? So our c sub n's are now going to be equal to 2 divided by a, okay, times the integral from a to 0 of what was on the left-hand side. In this case, I changed that m back to an m. So it doesn't matter because n and m are equal in this case. Okay, so I can switch it back. Okay, so what does it all mean? Okay, if you know what you set that hot plate at, okay, which is, that was boundary condition 3. Okay, you can solve for the coefficient c sub n's. That is the coefficient of each term okay, and you'll do that by setting n equal to 1, 2, 3, blah, 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 and solving that integral, okay, either by hand or using a computer, okay. When you're done, let me write that in red maybe. When you're done, the solution will look like what we had before. Now this is a specific solution because we know what these coefficients are. We've solved them, okay? And I'm going to add n terms, however many terms I need. It could be an infinite amount. It could be for special functions, maybe a finite amount. Okay, this would be our n equals 1 term. And I would also know what C2 is. This would be the C2 term, or the n equals 2 term. And I can keep going until I got the full thing. Okay, so thanks to Fourier and his brilliance, through this technique, we can find our last remaining coefficient and turn our general solution into a specific solution that fits all of our boundary conditions.